Let's talk about complex numbers. Let's talk about complex numbers kind of from the beginning, and we can see where it shows up in trig. So trig can make its entrance a little bit later into complex numbers. So the first place we want to think about complex numbers is we want to think back to when we first started learning about square roots. And way back in the day when we were learning about square roots, so like we learned that the square root of 4 is 2, the square root of 9 is 3. We start off learning our squares, the square roots of square numbers. Then we learn some of the cool stuff. So first we start learning the square roots of squares. Then we start learning some of the cool stuff, like the square root of 5 is irrational. That is, if we want to know the square root of 5, the best we can do is an approximation without just writing it the exact value. So 2.236 but this decimal representation of the square root of 5 never ends and it never repeats. So it's not a repeating decimal nor terminating decimal. So this decimal representation neither repeats nor terminates. Then we start incorporating these square roots into solutions of equations. So things like x squared equals 4 means that x is either positive or negative 2. We get the 2 solutions. So we start learning some stuff about square roots. Now, throughout this whole process, if we have the square root of a negative number, we said that is not a real number. So throughout this whole process, back at the beginning, we had the square root of 4, square root of 9, square root of 5 is irrational. But if I have the square root of a negative number, we said that's not a real number. And then that's where it was over. It was not a real number. In the context of an equation, we might see x squared equals negative 4, and we'll say this has no real solutions. This is how it would show up in equations. This is how it would show up in this computation. The square root of negative 4, we learned this is not a real number. At the time we learned this, we knew stuff like undefined, but we didn't use that phrase here. We said the square root of negative 4 is not a real number. We didn't say that it was undefined. We didn't say that there's no answer. We just said it wasn't a real number, which raises the question, if it's not a real number, what kind of number is it? And this is the important part. It's not a real number. There are no real solutions. So if these aren't real numbers, if we don't have real solutions, what kind of numbers or solutions are they? So this is typically what happens in math. We come across something and we could see why this is not a real number. Because if I take a real number and square it, it has to have the same sign as itself, right? So this makes sense. The square of a number, any real number, has the same sign as itself. So when I multiply a number by itself, the sign's always the same. So if I take a number and square it, this is just a times a. And a number has the same sign as itself. So it's always the same sign. And so if I have a negative times a negative, I get a positive. And if I have a positive times a positive, I get a positive. So a number has the same sign as itself. So if I take 2 squared, that's 2 times 2, positive 4. Because I have a positive times positive is a positive. But if I have negative 2 squared, that's a negative times a negative. That's a positive. So because a number has the same sign as itself, when we square a real number, we end up with a positive value. So no real number can be the square root of a negative number. So like most things in math, we're like, oh, well, what if not? Could we make this something else? And if whatever other thing that we invent, would that be nice and logically consistent? So we made something up. We, like I was there. If not real, then what? Sometimes this kind of thought leads nowhere. Say, here's a thing that you can't do in math. And mathematicians be like, oh, well, what if we could? Let's make something up to see if that is okay. And it turns out with complex numbers, we can. We introduce what's called the imaginary numbers. I wasn't in on the meeting where we decided to call this the imaginary unit, so I don't know if I like this name or if we're just stuck with this name. But that's what we did. We said real and imaginary. That's how we decided to name things. I don't know what I would have picked in its stead, but I just feel like this is something we've been saddled with, and I'm not sure it's a really good idea. But this is what we got. It does sound fancy. And this is what we made up. We, like I was there. Imaginary unit is the square root of -1. That is, I squared is -1. Clearly, I is not a real number. I is the imaginary unit. And we can alternately say I is the square root of -1, or I squared is -1. This is how we're going to use this then. So for example, if I wanted to calculate the square root of -4, we know that this is not a real number. This is going to be an imaginary number. The square root of, we're going to imagine this as a square root of 4 times a square root of -1. The square root of 4 is 2, and the square root of -1 is I. So that's what we're going to do. We've invented this new kind of number. that's going to be the square root of -1, and it'll show up when we try to take the square root of a -1. So if you see a negative under your radical, then we can pull out an I. And an imaginary unit I, not like pull out an I, otherwise you can only do two problems. If this shows up in an equation, we still get the plus or minus business like we always did. If I have an equation that says x squared equals -4, then we still get two solutions. X is equal to plus or minus 2i. We get those two solutions. If I take 2i and square it, two I squared is going to be 4i squared. I squared is -1, so that's -4. And if I take -2i squared, -2 squared is 4i squared is -1, so we get -4. This negative gets squared, but this negative at the end showed up from the I squared. So there are our two solutions to x squared equals negative. So we made a new form called the imaginary unit. Then we start wondering where this is going to show up. It showed up in this quadratic equation where x squared is equal to -4. So it shows up as the zeros of the polynomial x squared plus 4. Now, if we think about the graph of x squared plus 4, that's going to be the graph of a polynomial. That's going to be the quadratic graph or a parabola. And we know that the x-intercepts of a parabola are the real zeros of a quadratic. If we think about the polynomial x squared plus 4, we got these two zeros, but the zeros are imaginary. Plus or minus 2i, those aren't real numbers. No real zeros, no x-intercepts. So if we think about the graph of x squared plus 4, we get a parabola, but that parabola has a vertex above the x-axis. No real zeros, no x-intercepts. So when we set x squared plus 4 equal to 0 and solve to find the x-intercept, we don't find any real solutions, but we do find these complex solutions or these imaginary solutions. So the graph of x squared plus 4 is going to be a parabola with a vertex above the x-axis and it opens up. So it's never going to hit the x-axis. No x-intercepts, no real solutions, and this tells us so. Then we start moving things left and right. And we can bring this up now because this is a tricky class. We can start shifting things left and right. So notice that here we had the two zeros were of x squared plus 4 were imaginary, plus or minus 2i. They didn't show up as x-intercepts because we had they were imaginary. So there's nowhere to put them on the real number line. Remember that the x-axis and the y-axis are real number lines. There is no location that says 2i or negative 2i. Now, if I take this x squared plus 4 and I shift it to the right 1 unit, our vertex is at 1, 4. We still do not have real solutions or real zeros, so we still do not have x-intercepts. We just have this parabola. My parabola is melting over here a little bit. What's that? I think I've mentioned this before, but if someone asks you to describe a parabola, do not say it's a U-shaped graph. If you're going to try to draw a parabola like this without plotting points, don't try to draw a U. U's have vertical sides. Look at all the U's on our table of elements. All the sides on the U go vertical, but a parabola does not have vertical sides. It's got curvy sides that are very straight up and almost straight up and down, but it's more of a V shape. So in your mind, if you're drawing a parabola, don't draw a U, draw a V, and just round off the bottom. Don't draw a U, draw a rounded V. I don't know why I care about that so much. I think I just get annoyed when people say it's a U-shaped graph. That's not a U, that's a V. So all we've done here is move the vertex to 1, 4. Now let's look at the zeros of this polynomial. So if I set this equal to 0, x minus 1 squared plus 4 equals 0. We can solve by doing inverse operations in reverse order. So I'm going to subtract 4 from both sides. Now, before imaginary numbers, we'd be done. We'd be like, ah, look, no real zero. No x-intercept. That's still true. No real solutions. But now we have complex number technology. We have imaginary unit technology. So now if x minus 1 squared is negative 4, that means this x minus 1 is just plus or minus a 2i. Because now we have a square root of negative 4. The square root of negative 1 is I. The square root of 4 is 2. So here are the two solutions. X equals 1 plus or minus 2i. This number is a combination of a real number and an imaginary number, and this is a complex number. Question? It's doing something in the complex numbers that we can't see. That's right. This is the real axis, and this is another real axis. So we can't see. This is stuff happening in the complex number plane. It's the same way that when y'all look around this room, since you exist in 3 dimensions, you don't see all the 4-dimensional and 5-dimensional beings walking around. You can't see that. Those are the complex zeros. You can't see those complex zeros intersecting anywhere because we're looking in the real plane. There's a real axis. This is a real axis. There's nowhere to put plus or minus 2i. The 6-dimensional person isn't here today. I'm just kidding. I can't see in 6 dimensions. I can't see in 6 dimensions. I haven't had the right coffee today. There's a certain kind of coffee that you have to drink to see into the 6th dimension. And it doesn't last very long. 4 to 5 hours is is a pretty long time to be seeing in that. Any more than that, and it could drive you insane. So just be careful. Yep. That and all the lead that we are using in our gasoline. Yep. So here we have a combination of a real number and an imaginary number, and this is called a complex number. When we combine a real number and an imaginary number, we get what's called a complex number. The complex number system is a number system that is a superset of the real number system. We learn about real numbers, then we learn about rational numbers as a subset of the real numbers. We learn about the integers as a subset of the rational numbers. We learn the natural numbers as a subset of the integers. And sitting above all that is the complex numbers. So there's all the complex numbers. The real numbers are, all real numbers are also complex numbers. So we've invented a new unit, this imaginary unit, to be the square root of -1. And this has led to the existence of these complex numbers. So a complex number has a particular form. A complex number has the form a plus bi. There's a real part and an imaginary part. A and b are both real numbers. The imaginary part is made imaginary by the I. That I factor is what makes it an imaginary number. A is the real part and B is the imaginary part. It's a number that has two parts. This is not a very big concept. We've had this before. Fractions are numbers with two parts, a numerator and a denominator. Ordered pairs are numbers with two parts, an x-coordinate and a y-coordinate. Or if you want to be fancy, an ordinate and an abscissa. I don't know which one is which, but I know that those are the two words that we try to do. I don't know which one is the ordinate and which one is the abscissa. But it's just a number with two parts, the real parts and the imaginary part. Note that A and B are both real numbers. No, B is the imaginary part, BI is the imaginary term. Yeah. So now that we have these complex numbers, we have to they're just numbers. And so we need to be able to do all of our normal number things with them. We need to be able to add them, subtract them, multiply them, and divide them. We need to be able to perform operations on complex numbers. Complex numbers look like polynomials. It's just polynomials with extra root. So I is the square root of -1. I is just I. I squared is -1. Here's what we're going to notice about I. Anytime I have a power of I, it's always going to be plus or minus I or plus or minus 1. Let's look at I cubed. Let's take I squared and multiply it by I. So I cubed is just I squared times I. I squared is -1. So instead of writing I cubed, we'll write -I. If I write I to the fourth, I to the fourth is just I squared times another I squared. That's just -1 times -1. That's +1. So instead of writing I to the fourth, we'll just write 1. If you don't like I squared times I squared, I can just take -I and multiply it by I. I'll get -I squared, but I squared is -1, and I'll get +1. It's good when things are consistent like that. If you do a problem 2 different ways and you come up with 2 different answers, one of those ways is wrong. In math, you don't get to agree. I is just I squared is -1. I cubed is I to the fourth is 1. These are all the things that we need. Because once I get to I to the fifth, I'm back at the beginning. So I to the fifth is just I to the fourth times I, but I to the fourth is 1. So I to the first is the same as I to the fifth. And now we are in a loop. I to the sixth, I can take out I to the fourth. I to the sixth is I squared. I to the seventh is I cubed. I to the eighth is is 1. I to the ninth is I. I to the 10th is I squared, or -1. I to the 11th is -I, and I to the 12th is 1, and so on. So we only need these 4 values. I, -1, -I, 1. And then we just repeat. Is what 2? Oh, no, I'm just making music notes. I'm just using a repeat sign. I'm just messing around. These are the 4 that we need. And the one that we use is whatever the remainder is when we divide by 4. 5 divided by 4 has a remainder of 1. So I to the fifth is I to the first. 12 divided by 4 has a remainder of 0. So it's I to the 0, which is 1. And there are only the 4 possible remainders, 0, 1, 2, or 3. Now to tell us if we have an I, so in order, a 1, an I, a -1, and -5. No, because I cubed comes out -I.
None of them.
I'm not sure what you're asking. What what this is telling us is that anytime we have a power of I, like if I see something and it ends up being like I to the 17th power, that can be any power of I can be reduced to one of these 4 answers. If we have I to the 17th, if we have I to the 17th, 17 divided by 4 will have a remainder of 1, right? Because this is an I to the 16th times I to the first. I to the 16th is equal to 1, and I to the first is just I. So I to any power is one of these 4. We can think about it that way. When we multiply by I, then if we make a complex plane where the real is horizontal and the imaginary is vertical, which is exactly what we do. And if we multiply by I, it'll just rotate everything 90 degrees. But these are the 4 things that can happen if you take I to raise it to a power. That means we never have to have I raised to a power. This is what this means for dealing with complex numbers. If I decide to multiply a couple of complex numbers, if I decide to take, for example, -1 plus 4i and multiply that by 2 minus 3i, I can treat this just like a polynomial. When I multiply these two numbers, I'm going to end up with the I squared, but I squared is -1. Get rid of that. And I'll end up with just a complex number. But as far as what we do to multiply, it's the same thing that we always do to multiply when there's more than one term involved or more than one digit involved. -1 times 2 is -2. -1 times -3i is +3i. 4i times 2 is 8i. 4i times -3i is -12i squared. Just like we would if they were polynomials. Just like they would if you were polynomials, I've got a 3i and an 8i, that's going to make an 11i. But -12i squared, since I squared is -1, -12i squared is actually +12. So -2 plus 12 is going to be 10. So when I multiply these two complex numbers, I get that complex number, 10 plus 11i. I squared is equal to -1. So that's up here. This is I is equal to just I to the first. If we have an I squared, that's -1. I to the third is -I, and I to the fourth is 1. So anytime I see I squared, I want to get rid of that and replace it with -1. So this is going to be -12 times -1. Since I squared is -1. -12 times -1, +12. +12 and the -2 make a +10. On the previous page, we saw that we take -2, if we take a 2i and square it, we get 4i squared or -4. So if I take one of these numbers and square it, like 2 minus 3i and square it, I have to square it just like I would a polynomial, because that's all these numbers are, just polynomials with some extra rules. So I'm just going to do 2 minus 3i times another 2 minus 3i. So 2 times 2 is going to be 4, minus 6i, minus another 6i, plus 9i squared. -6i and -6i will be -12i. And then this 9i squared is -9. So this is going to be +9 times -1, or -9. 4 minus 9 is -5. We're just doing the same thing with polynomials because that's all numbers are. It's just polynomials. Just this was 20 -3 squared. 20 -3 times another 20 -3. Multiply first out of there last. Same thing we always do. Now, one thing we'll note is that if we ask our calculator something like, what is the square root of -4? I don't know, actually. Let me double check. Oh, that's good. It says error, non-real answer, not no answers, non-real answer. If we're going to be asking for complex numbers, if we want our calculator to deal in complex numbers, we have to warn it ahead of time. Right now, the calculator is saying, no, I am set to real numbers only. So get out of here with that stuff. But if we go into the mode and scroll down, instead of highlighting real, I can switch over to A plus BI. Now my calculator set is going to be okay with complex numbers. So now, if I say, hey, calculator, what's the square root of -4? It'll be like, oh, 2i. Now I can use complex numbers on my calculator. That is on the mode, scroll down from real to A plus BI. And then highlight that. Now, if I want to do some calculations, the I button is right above the decimal point. There's an I, and that's our imaginary unit. It's in blue, so I have to press my blue second button. But then I can multiply if I want. So -1 plus 4i, I'll put in parentheses, -1 plus 4 second decimal point, extra parentheses, times 2 minus 3 second decimal point, close parentheses, 10 plus 11i. I've told the calculator, hey, we're going to do some stuff with complex numbers, and we're going to do it in rectangular form, A plus BI. So now my calculator's in full. Cool, I can do that. If I take 2 minus 3i and square it, there's the -5 minus 12i that we calculated by. If we have irrational numbers, irrational imaginary numbers, it writes the decimal and then just puts an I at the very end. You don't have to write all those digits to write the square root of 5 or I times the square root of 5. Or we can stop writing the decimal approximation, put an I there. Is that okay? I just squared things here, but we can also, now that we have calculators, and I don't have to do as much polynomial stuff, if I did 2 minus 3i cubed, I get -46 minus 9i. Once again, nothing is changing. I'd multiply these first two, and then I would multiply that by 2 minus 3i. So I get -10 plus 15i minus 24i plus 36i squared. You should make sure that in the mode, you're in the middle one, real, and then A plus BI. Otherwise, it'll try to put it in polar coordinates, and we want it in rectangular coordinates. But degree is, we're not doing anything with trig functions or angles, so it should be returned in the same value. You might have a decimal point or a Make sure you're using the right change of the sign or subtraction. Any questions? So we treat complex numbers just like polynomials, but we don't need all the powers of I. Anytime we have a power of I, we get out. Plus or minus 1 or plus or minus I. That's ever okay. This is a crash course in complex numbers. This is what you all did back in algebra. Like, oh, I don't remember doing this back in algebra. When I ask questions, I go, hey, remember complex numbers from algebra? They're like, well, hang on, is there a quiz on complex numbers today? And I'm like, oh, no. And you're like, oh, then totally I remember complex numbers. Like, oh, should I skip the reviews? I go, no. I want to see what you think about that. So why don't you go over that? Just, make sure we're all on the same page. You said no quiz, right? Yeah, no quiz. All right, yeah. Let's see if we're all on the same page. So the first place you recall encountering complex numbers is when you were solving quadratic equations. Because in a polynomial equation with real coefficients, you'll either have real solutions or complex solutions. Complex solutions always come in conjugate pairs from some quadratic. Yes. Conjugate means plus or minus in the middle. Real part plus or minus the imaginary part. If a polynomial has real coefficients, it'll have complex zeros in conjugate pairs. Conjugate pairs are plus or minus. So a conjugate pair would be like A plus or minus BI. If A minus 2, minus 3I, sorry. If 2 minus 3I is the solution of the polynomial, then 2 plus 3I is also a zero of the polynomial. I think I said solution of the polynomial. Zero of the polynomial. This shows up in our quadratic equation. In our quadratic equation, we have negative b over 2a plus or minus the square root of b squared minus 4ac over 2a. The square root is where we might get the imaginary part. So here is the part that's going to definitely be real if b and a are real. But this part, this second term, the plus or minus term, has a square root in it. B squared minus 4ac might be less than 0. So this is where any imaginary stuff will show up. All right, let's take a quick break, come back and then talk about these solutions, talk a little bit more about complex numbers, and then try to maybe find out when trigonometry enters the chat.